Hello everyone, welcome to Probability and Statistics for Data Science. Today we will explain how to perform causal inference using linear regression. First, we will show that confounding factors can easily distort observed linear effects in the data. Then we will demonstrate that including those confounding factors in the linear models can neutralize them and allow us to estimate the true causal effects. Let's get to it. So we're going to talk about causal inference via linear regression, and we're going to use this real-world data set from Spain as an example. So these are monthly data recorded in Spain between 2015 and 2022. On the y-axis, you can see the unemployment in millions during that month, and on the x-axis, you can see the temperature. So for example, in this month, the temperature was 60 degrees Fahrenheit, and the unemployment was 3 million. We immediately see that when the temperature is high, the unemployment tends to be low, and when the temperature is low, the unemployment tends to be high. Our goal is to determine whether there's a linear relationship between unemployment and temperature, and a natural way to do this is just to fit a linear regression model where the response is the unemployment and the temperature is the feature. If we do that, the linear coefficient associated with the temperature is equal to minus 0.01. This might seem small, but that's just because temperature is measured in degrees Fahrenheit, which are an order of magnitude larger than the millions that we use to measure unemployment. And because of that, if we standardized both quantities, the coefficient would actually be minus 0.21, which is the correlation coefficient between unemployment and temperature. So it's quite substantial. We definitely observe a linear relationship between these two quantities where when the temperature is high, the unemployment is low, which we had already determined visually. But the key question here is whether that linear relationship that we observe in the data actually reflects a causal relationship between temperature and unemployment. If we were able to decrease the temperature in Spain, would that increase unemployment? Or said otherwise, if we see that next month the forecast is that temperatures in Spain are going to be abnormally high, should we expect the unemployment to drop as a result? Common sense indicates that this probably will not be the case, but we're going to understand why and what to do about it. So in causal inference, the key question that we try to address is, does a certain variable of interest that we call the treatment cause a certain outcome that is the variable that we're actually interested in? So in our example, the outcome would be the unemployment and the treatment would be the temperature. The way we analyze this question mathematically is by defining the potential outcome, which reflects the value of the outcome for any possible value of the treatment, whether it is observed or unobserved. In the observed data, we only get to see the treatment for the value that is actually we only get to observe the outcome, not the treatment, the outcome for the value of the treatment that actually happened. Here, t with a squiggly line on top is a random variable that represents the values of the treatment that we actually get to observe. So this would be the temperatures that we see in Spain. When that is fixed to a specific constant, then that is the potential outcome that we get to see. And this is the fundamental problem of causal inference. The data are highly incomplete. If the temperature in Spain is 40 degrees, then we get to see the potential outcome associated with 40. We do not get to see what the unemployment would have been that month if the temperature had been 45, 30, 63, 75, etc. All of these other potential outcomes that we do not get to see are counterfactuals because they are counter to factual reality. And it's really a pity that we don't get to see them, because if we did, then we would immediately be able to identify whether there is a causal relationship between the treatment and the potential outcomes. Let's take a look at a toy example where the potential outcomes do not change if we change the treatment, but it's kind of difficult to determine that is the case because of the fundamental problem of causal inference. So here, for this sample of the potential outcome, it's equal to this. The treatment was equal to this. If we had changed the treatment to this, the outcome would have been the same. If we had changed the treatment to this, the outcome would have been the same. Here, the potential outcome does not change with the treatment. If the line was like this instead, then there would be a causal relationship between the treatment and the potential outcome, but the actual observed data would be exactly the same. Okay, just to be clear. Here, this is another sample of the potential outcome. Again, the potential outcome does not change with the treatment, but we see a different sample because of other factors that affect our potential outcome. Here the same, we only get to see this observed outcome. In this particular case, if we had changed the treatment, it would not have modified the outcome, but we only get to see that point. In a moment, we will see that is why that can be very problematic. We define a linear causal effect when the mean of the potential outcome is proportional to the treatment with this constant of proportionality, which is what we want to find out. If that constant is positive and very large, this means that when the treatment increases, the mean of the potential outcome really increases. When that constant is negative and large, then if we increase the treatment, this will produce a large decrease of the mean of the potential outcome. So, why are observed linear effects not always reflective of true causal effects? So we already explained this in the video on correlation and causation, but I want to repeat it because it's very important. Well, the issues can arise when the treatment is dependent on the potential outcomes. So here you see that for each specific sample, if we had changed the treatment, it would not have changed the potential outcome, but we're actually choosing the treatment to be large when the potential outcome is large. And we're choosing the treatment to be small when the potential outcome is small. This is like giving medicine to the healthy people and not giving medicine to the ill people. What's the problem? When we look at the data, it looks like the medicine works, even though it does not. Okay, so if we had chosen this point to be here, then we wouldn't be seeing this linear pattern. This linear pattern is due to the fact that the treatment and the potential outcomes are dependent. The treatment was chosen to be large when the potential outcome was large and small when the potential outcome was small, which induces this spurious linear relationship between the treatment and the observed outcome. This would not happen if the treatment was independent from the potential outcome, which can be achieved by randomizing the treatment. Let's continue to explore this in a bit more detail by defining an idealized model where the potential outcome depends linearly on the treatment, but also on a confounder. So here the potential outcome depends on the treatment with a certain constant of proportionality beta, but it also depends on a confounder C and on some additional factors that are not connected to the confounder or the treatment. What we actually get to observe is exactly the same thing, but here we're plugging the observed value of the treatment. Okay, remember, this is just a constant that we could change to whatever we want to obtain the potential outcome, but we do not see all the potential outcomes. We only see the one associated with the value of the treatment that we actually observe, which is why here we plug in the observed value of the treatment. Now our assumptions are going to be that T and C are standardized, so everything is centered to have zero mean, and the effect of the treatment is determined by this coefficient, and the effect of the confounder is determined by that coefficient. And also, this additional term C is independent from T, from the treatment and from the confounder. So, as we will see, it doesn't really have like an effect on our analysis. But this is just to show that there can be other factors that are affecting the potential outcomes, but are unrelated to the treatment and the confounder, and that's fine. Okay, so what we really want to do here is estimate the linear effect of the treatment on the outcome of interest. A reasonable way to do that is by fitting a linear regression model as we did for unemployment and temperature, where the response is y, in our case unemployment, and the feature is t, in our case temperature. If we do that, then the minimum mean squared error estimator of y given t, okay, which we denote by this, is going to be equal to the covariance between the outcome of the treatment divided by the variance of the treatment. We already proved this in the video on minimum mean squared error estimation. And notice that here we have just one feature. So when we do ordinary least squares and we look at the coefficient, it's going to be very close to the minimum mean squared solution, because we're going to typically have much more data than just one data point, and we only have one feature. Okay, this is just in case you're worried about the fact that OLS is the ordinary least squares solution computed on data. That's not always approximate the minimum mean squared solution. This is not a factor here. This is not a problem here because we have so few features. Okay, so we have seen that we have standardized the treatment. So this is just going to be equal to 1. And the linear coefficient that we observe between the outcome and the treatment is just equal to their covariance. And in the video on correlation and causation, we saw that because of the presence of this confounder, here we're not going to just observe the coefficient corresponding to the treatment, we're also going to observe the coefficient corresponding to the confounder and the covariance between the treatment and the confounder. So if the treatment and the confounder are correlated, we have a problem here. Okay, the confounder distorts the linear coefficient that we observe. Let's make this very precise with this simulated example where we have this guinea pig rescue. This is an example that already appeared in the video on correlation and causation. What happens here is that the guinea pigs are very thin, and the personnel of the guinea pig rescue wants to fatten them up. And in particular, they want to determine whether a nutritional supplement is helpful in increasing their weight. So here, our potential outcome of interest is the weight change of the guinea pigs. Because I made up this example, I decided that the supplement was going to be useless. I don't really believe in supplements that much. And the weight change only depends on a confounder and some other factors. We'll see what the confounder is in a moment. So when we actually observe the weight change, we're only observing changes in the confounder and in these other factors. The treatment here is the supplement intake, and it has no effect on the potential outcomes, so the true causal coefficient is 0. This is the coefficient that we would like to estimate from data. There is a confounder, which is the food intake, how much food guinea pigs eat. The more they eat, the more weight they gain, so the coefficient here is 1. Okay, to indicate that if they eat more, they gain more weight. When we fit a linear regression model of the potential outcome just given the treatment, the coefficient, as we saw a moment ago, is equal to the coefficient corresponding to the treatment plus this term, which in this case corresponds to the covariance between the treatment and the confounding factor. In our example, the first week, the guinea pigs are fed the supplement mixed with the food. And because of that, the supplement they eat is actually correlated with the food they eat, because the ones that eat more food eat more supplement because it's mixed with the supplement, and the ones that eat less food eat less supplement. This induces a covariance, so the covariance between the treatment and the confounder here is 0.8. We saw that this is going to induce the same covariance between the supplement and the outcome of interest, and indeed that's the case. The covariance between them is also 0.8. You can see that from the shape of this scatter plot, and you can also see what is happening. For large values of the supplement, those are precisely the pigs that had more food intake, as you can see from this color code, and those are the pigs that also gain more weight. The pigs that ate less supplement ate less food, as you can see here in the color bar, and hence they gained less weight. So this is a spurious correlation that is reflected in the linear coefficient, which is going to be equal to 0.8. And that's the linear model. If we fit a linear model where the response is the weight change, our outcome of interest, and the feature is the treatment, the supplement intake. The second week, they gave the supplement to the guinea pigs after the guinea pigs ate their food. And because of that, now the amount of food they ate was negatively correlated with the supplement, because the ones that ate more food were not hungry anymore. So then they ate, these are the ones that ate more food. They ate less supplement because they weren't hungry anymore. The ones that ate less food ate more supplement because they were still hungry. Maybe they fight for their food or something, these imaginary guinea pigs. So then, as we saw in our formula, this is going to induce a spurious correlation between our outcome of interest, which is the weight change, and the supplement intake. Why? Because the pigs that eat more supplement are eating less food and so are gaining less weight. And the guinea pigs that are eating less supplement were actually eating more food, and so we observe that they gain more weight. So this could make us mistakenly conclude that if they eat more supplement, they're going to gain less weight. The supplement is somehow hurting them. If we fit a linear regression model, as we had established before, the linear coefficient is going to be equal to minus 0.8. We determine an incorrect linear relationship between the weight change and the supplement, between our outcome of interest and the treatment. This is because we have performed a short regression where we have only included the treatment. In general, this we will see in a moment why this is called a short regression, by the way, in case you're wondering, but you can start thinking about why that might be. The issue that we have encountered is that the linear coefficient is distorted by the confounder. Okay, so how could you solve this problem? Maybe pause the video and think about it. And if you've watched the video on why correlation does not usually imply causation, well, there's a solution here, which is we could just randomize. If we randomize the amount of supplement that we give to each guinea pig, or in general, if we randomize the treatment, then that is going to neutralize every possible confounder, because there will be zero correlation between the treatment and the confounder, because we are randomizing the treatment, so it cannot be dependent on some other quantity. However, this is often costly, or it may even be infeasible to feed like a random amount of supplement to each of the guinea pigs. It can be just much easier to give them supplement in general and then measure how much each of them ate. This is common in many situations. In particular, in our Spain example, we cannot randomize the temperature that occurs in Spain. Whatever temperature there is, that's what it is. So these are observational data where we cannot randomize. In those cases, we have an alternative to try to neutralize confounders that we actually observe. This will not work for confounders that we cannot observe. What we can do is we can adjust for those confounders or control for those confounders by including them in the model. So let's see what happens in our example when we do that. So now we're going to fit a linear regression model where the response is still the outcome of interest, but now our feature vector is not only t, it also includes the confounder c. So this assumes that we know what the confounder is, and two, we can actually measure it in each of our data points. In the case of the guinea pigs, we actually have to measure how much food each of the guinea pigs ate, not only how much supplement they ate. So now, if we fit this long regression model, long because now it has more features, we will see that it actually controls for confounders under the assumptions that indeed the observed outcome only depends on the treatment, the confounder, and then other unrelated quantities. We're going to represent the features by x here. This is a random vector that includes t and c. So the mean squared error estimate now is a little bit more complicated because there's not only one feature, there's more than one feature. This is no longer simple linear regression. In our video on minimum mean squared error estimation, we saw that the linear coefficients are equal to the inverse of the covariance matrix of the features times the cross covariance between the features and the response. So in this case, what is the cross covariance between the features and the response? Well, we multiply each of the entries of X with the response Y, and we take the mean, and Y is equal to this by our assumption. So when we multiply this out and apply linearity of expectation, we get these terms. The mean of X transpose, which is just the covariance matrix because the coefficients come out by linearity of expectation, and the mean of X times C. But we are assuming that C is independent with both features, so this is just the product of the expectations, and we're assuming that these guys have zero mean. So we're left with the covariance matrix times the true coefficients. I probably have written it down there exactly, and now we just plug it in here, and the inverse of the covariance matrix is going to cancel with the covariance matrix. We actually identify the true causal coefficients under the assumptions that the outcome indeed only depends on the treatment, the confounder, and then these unrelated factors that are independent from them. So it works. The long regression actually manages to identify the true causal coefficients. And now we're going to see that that is the case for our simulated guinea pig data. So here, remember that our observed outcome of interest only depends on the confounder, does not depend on the treatment. The coefficient corresponding to the treatment is 0, and the coefficient corresponding to the confounder is 1 because when they eat more, they gain more weight. And the confounder is the food intake. So in the first week where the supplement was mixed with the food, the issue we had was that we saw this short regression coefficient of 0.8 because of the positive correlation between the supplement and the confounder, which is the food intake. So now what do? We incorporate the food intake. Now we have to measure food intake for each of the guinea pigs. And we're going to fit a linear regression model which has two features, the food intake and the supplement intake T. Okay, and here the response is color-coded. So what happens? What happens is that these are so on these lines, on these contour lines, the linear model is constant, and we see that the weight, according to the linear model, the weight change increases when the food intake increases, but is constant with respect to the supplement intake. So because of including the food intake into the model, now we see that the supplement actually has no influence. We correctly see that as this model satisfies the assumptions in our analysis. So just to be clear, these are the guinea pigs that are gaining more weight. We see that they also take more supplement, but the model correctly identifies that this is because of the food intake. The second week, the supplement was provided after the food, so the amount of supplement was negatively correlated with the food intake, which in turn caused a spurious negative correlation between the supplement and the weight. In order to neutralize this, we include the food intake again. So here we see the negative correlation between the supplement and the food intake, and now we're going to fit another model where the features are the supplement and the food intake, and the response is the weight change. So we see here weight change is higher here and lower there. The model again correctly identifies that this just depends on the food intake, right? The higher the food intake, the higher the weight change, but it's constant with respect to the supplement because we have included the confounding factor within the linear regression model, and consistent with our theoretical analysis, this yields the right causal coefficient associated with the treatment, with the supplement intake. So now let's go back to our example with unemployment and temperature in Spain. If we fit a simple linear regression model, which is a short regression because we're not including other stuff, then we have this coefficient, which again, if we standardized everything, would be minus 0.21, so a substantial negative linear relationship between temperature and unemployment. But maybe there's a confounder that is governing this. And what do you think that is? If you've watched the video on correlation and causation, you already know. Well, this confounder is tourists. For these values of the temperature that are high, the number of tourists that visited Spain was really high, and this decreased unemployment because tourism is a big industry in Spain. For these values of temperature that were low, maybe I'll use another color, low temperature, high unemployment. Why? Because less tourists. So what can we do so that this is reflected, so that we can actually identify this in our linear model? We include tourists in our linear model. So here we're showing tourists in the vertical axis and temperature in the horizontal axis, and you see a correlation between temperature and tourists. And now we fit a model where the response is unemployment, and these are the two features. And the model correctly identifies that more tourists, less unemployment, but the relationship with temperature is essentially constant. The coefficient is much, like 2 orders of magnitude smaller, and it's actually positive now instead of negative. So this is a clear indication that once you take into account tourists, there's no real relationship between temperature and unemployment. To drive this point home, let's do an analysis of the variance explained by these different linear models. The fraction of variance explained by the model that only included temperature had an R squared, a coefficient of determination of 4.2%. So only temperature explains 4.2% of the variance in the unemployment, which is, for economics, this is definitely something. But the problem is that when we look at the variance explained only by tourism, it's 0.12, it's much larger. And the key observation is that if we do temperature and tourism together, then the variance, the additional variance explained, like the difference between the model that only uses tourism and the model that uses temperature and tourism, is minuscule. So this is a strong indication that this R squared, this coefficient of determination here, is just due to the fact that temperature is correlated with tourism, as we saw in our analysis, where the coefficient associated with temperature, once we include tourism, is almost 0. So this is very strong evidence that temperature and unemployment are not causally related, and that they only seem related, they are linearly related because of this confounding factor that is the number of tourists. So what have we learned? We have learned that unobserved confounders can completely distort linear coefficients in short regression models that don't include those confounders. We can adjust for the confounders that we actually observe and know about by including them as features in long regression models that are called long because they include those confounders. And this works as long as the linear assumptions hold and as long as there are no additional confounders. And that's all I got. Thank you very much.